To introduce to you Da-jun Zhang from Shanghai University. We'll talk about Sylvester equation, Cauchy matrices, and matrix discrete systems.
Okay. Thank you, Yaron. And first, I think I should thank this institute and also organizers for both the program in 2009 and this workshop. So this work just started from 2009, the program, and it takes 4 years and up to now. So first, what is Sylvester equation? So Sylvester equation is a matrix equation like this, and A, B, X, and C. All of them are matrices. So actually, Sylvester is the first person who defined as well as gave the name matrix. That was in 1850, and then in 1885, it proved the condition that this kind of equation can have unique solutions. So the condition is the matrix A and the matrix B, they don't have same eigenvalue. This is a Sylvester equation, and actually this equation is almost the most famous equation in the area of matrix theory. It has numerous applications, like in control theory, signal processing, and so on. And in dynamical systems, this is also famous equation. It's a special case of Sylvester equation. It is called Lyapunov equation. And usually for this kind of equation, it has exact solutions, but the solution is expressed by integral. Okay, so my talk is on the question is how is the Sylvester equation related to discrete integral systems? I suppose everybody knows these notations in discrete, and NM and shift in one direction, and we use tilde, and also hat in another direction. And so I like tilde hat notation, and I will use them in this talk. One example is lattice potential KdV, and another is discrete boostless KdV. And if this equation we look it as some three-component equation, then it defined on a basic square. Sylvester equation is related to the Cauchy matrix approach, and this approach you can find from this paper in 2009, and written by Frank Neyhoff and James Atkinson and Jarmo Hedrina. And in that paper, there is a detailed procedure on how the Cauchy matrix approach works. I will quickly reveal this approach. And this is kind of a Cauchy matrix, but in symmetric form, because this is a symmetric matrix. And we need start from this kind of matrix. Actually, we have rho I here. Rho I is a plane wave factor in discrete case. This is a discrete exponential function, and Cj is some constants. So if we introduce the diagonal matrix, this capital K, and this is a vector, and this is another constant vector, and we have this kind of equation. This is already Sylvester equation. But all of these elements are known. Plane wave factor and this matrix I, but they are satisfying Sylvester equation. And then, since Here we have independent discrete variables n and m, and we can have this kind of shift relation for plane wave factor, and we can have shift relation for all of these for the matrix M, and also for the shift of plane wave factor. So anyway, we have these relations, and the next step we can use in M, K, C, and R to define some scalar function. This is one scalar function, and then from this relation, so one can find this recurrence factor structure for these scalar functions, and also we can prove this scalar function is symmetric in terms of I and J. And then from this relation, we can choose some special value for I and J, and we can find some closed form. These are some examples. So one example is we take ij 0 and 0, and we call this function is W, and we get lattice potential KdV equation. And this is a lattice potential modified KdV. This is a Schwarzen KdV equation. Okay, all of these equations, their solutions are known because C, K, M, and R, all of these are known. So that means once we have these solutions from this equation from this approach, their solutions is already known. So one can also define this kind of scalar function with two parameters A and B, and it's also symmetric in terms of A and B, and such scalar functions satisfy this kind of recursive structures. And from these two, one can get this equation. This is called NQC equation. It's made of Quisberg and Capel. So this equation is quite useful. Actually, we derive this equation, and it's the solution of this equation is already known because all of these are known, as I said. It is useful because there is a transformation. This transformation is given in this paper in the I just mentioned before. There is a transformation, transform the NQC equation to the Q3 equation. So that means we already have solutions for NQC equation, and then using this transformation, we can get a solution of Q3, and more, because from Q3 there is some degenerate relation. That means all of these equations can be derived from Q3. So all of the solutions of these equations already known. This is the result in this paper. So next, what kind of generalization we can do? And first, let's look at solutions. Remember, in the Cauchy matrix approach, we have this kind of Sylvester equation, and we also have these two. These two are the relations for the plane wave factor, and we also these two. So suppose that now we suppose all of these are unknown. I mean, the M and R are unknown. M is unknown matrix, R is unknown vector, and we just start from these 5 equations. What can we have? Or what kind of discrete systems can we get? Actually, our starting point is just these 3 equations. The last 2 are not necessary. We can derive them from the first 3, and we need to use this kind of results. This result is proved by Sylvester. Is something like this: a homogeneous equation has 0 solution when k and minus k don't have same eigenvalue. And then we just use these two equations, we can derive this. We can have this. And compare these with this, and actually this blue part is nothing but a, and then we can get a must be 0. Then we have this. This is exactly same as this. So now our starting point is one Sylvester equation and two equations. This equation is used to define plane wave factor. But remember, M, R, here, M and R are unknown. We can suppose K, because K is some constant matrix, and C is also constant vector. So M and R now are unknown. And then starting from these three equations, we can have this relation. These relations are exactly the same as before. And then that means we can get same closed form for Sij and Sab, and then we can get same equations. That's lattice potential KdV, modified KdV, Schwarzen KdV, and NQC equation. But at this moment, M and R are unknown. So next question, we have to solve this equation side. How to solve it? Because this is a Sylvester equation, but so far there is no explicit form for this equation, because all of the solution of this kind of equation are given by some integral form. So we will find explicit forms solution for this equation. So let's do that. And first, we try to simplify this three equation side. Let's consider K is some similar form of K1 is similar form of K1 and K are similar, and T is some transform matrix. And then look at the equation for M1 K1. M1 is defined as this, and R1 C1 defined as this. So look at the equation for M1 K1 R1 C1. So they are exactly the same as them. So that means we have same equations. And further than that, actually, we can have same scalar functions. So if you look at the definition of Sij, you will find CKMR and C1K1 M1 R1. Same structure. That means any similar form of K will lead to same Sij and Sab, this kind of scalar functions. So that means we only need to consider the canonical form of K. So here we suppose gamma is the canonical form of K, and then we solve this. And first, if gamma is diagonal, and the solution is easy because it's exactly the same as before. And but look at here, we rewrite the matrix M by the product of three matrices, and the G is Ki 1 over Ki plus Kd. Okay, so next, if gamma is a Jordan block, how to solve it? First, we can get these two solutions of these two equations for R, and R is in this form. This is easy. And next, we have to solve this, because now gamma is Jordan block form, it's Jordan form. And we need to use some auxiliary matrices. This kind of matrix is called lower triangular Toeplitz matrix. Actually, all of these kind of matrices are commutating. So they commute each other. And remember, the Jordan block is also the Jordan block matrix is also same structure. So this is a Toeplitz matrix, and now we define F is this kind of matrix. It is also a lower triangular Toeplitz matrix. If we introduce I here, this is a vector, and we can express R. R is a solution. We have get it. We can rewrite R in this form. It's a product of F and I. And we also need another matrices like this. This is not lower triangular. This is, and although this is not Toeplitz matrix, but use this kind of matrices, we can express the vector C in this form. And also, such matrices have a property like this. If A is a lower triangular matrix, a lower triangular Toeplitz matrix, so they don't commute, but if they switch their position each other, and we have to add this transport here. Okay, now let's solve this. Remember this equation, if gamma satisfies some condition, and then it has unique solutions. So now that it has unique solution, we can suppose M in this form, because the solution is unique, and once we get solution, then it is solution. So F is a product of three matrices, F, G, and H, and F and G are defined as I just introduced. And then this Sylvester equation can be written in this form. And remember, we have this kind of property, so we can switch the position of H and gamma, and then we have this, and F and H can be cancelled, and then we can this. This is simple enough, because gamma is just a Jordan block, and on this side it's also very, very simple. So this can be exactly solved. And the solution of G can be expressed in this way. So any elements of in this matrix can be given in this, can be exactly given our okay. So now we have solved this. We have solved the Sylvester equation, and this is a simple comparison. Let's look at the let's look at the case of n is 2, the second order matrix. In diagonal case, this is soliton solution. Actually, give soliton solution, and in Jordan block case, and we have this kind of iron. Just some remarks.
Sorry, Da-jun, could you just go back to the previous one? So, okay, so the row 1 comes in front, is that?
Row 1, yes, this is row 1, and this is this is it1 times row 1, and it1 is this is a polynomial of n and m.
Okay, so the matrix does not depend on. Sorry, oh yeah, it does.
So this is matrix. This is row 1 is here.
Yeah, yeah. So what kind of solution does that correspond to?
This is correspond, if you look at the solutions from direct linearization approach, this corresponds, the integral has a double pole.
Okay.
Poles. And if gamma is a generic canonical form, it's some combination of diagonal and Jordan block, it's easy to write out the explicit forms of the solutions. And also remember, when we derive the solutions, equations, we need this kind of symmetric property, and this can also be proved using this kind of relation. So we have solved the Sylvester equation, and that means we can have the explicit form for Sij and Sab, and that means we can have new solution for NQC equation, and then we can have some Q3 and Q2 and some solutions for some equations in the ABS list. So the third part. Now let's look at more results. This is an example of discrete Busnesq. If we look at the solution of discrete Busnesq equation, and the plane wave factor is defined as this. Actually, we try to look for the dispersion relation in discrete case. But how to define discrete dispersion relation for this kind of lattice equations? Because M and N are always in some symmetric shape. So I think one way to consider the dispersion relation is we can relate the plane wave factor and the roots of a polynomial. So for the second order polynomial, the plane wave factor will be used to construct solution for ABS list for the second order equations, or NQC equations. For the third order polynomial, their roots will be used to construct solution and equations of discrete Busnesq type. So we have done some examples from binary approach with Jarmo Hedrina and for discrete Busnesq type equation, and also with Songlin and Frank from Berlinization approach to the discrete Busnesq equations. So next, let's suppose our starting point is still the series equation, but it is in the more general form. And we try to construct some matrix discrete systems. So that means we need to introduce some matrix polynomials like these, and this is just replace this scalar k by matrix k. And also, it's quite natural to define the roots in the scalar k, in the matrix case. If this is, for example, this is roots of polynomial scalar form, and this will be the same structure. Just replace this matrix with this number with matrix. The question is how to arrange these roots in the Cauchy matrix approach. So we can define this big diagonal. This is actually the block diagonal matrix, and K1, K2, KL is all of them are diagonal, are also matrix here, and this is K prime. We put our other roots in K prime, and then now remember K and K prime are roots of the polynomial. We use them to define plane wave factors, and this is Sylvester equation. So we use this phi equation as our starting point, and then we introduce some vectors. Actually, this is some matrix vector, and this is some matrix scalar function because it is matrix. But we will use them to generate matrix equations, and then we will find some shift relation for U, and using this kind of shift relation, and we need also define more these matrix scalar functions, and then we will get this shift relation for this kind of functions, and then from their closed form, we can find some discrete matrix equations. This is the procedure, and the results is the following. This is matrix lattice potential KdV, and here alpha 1 is a parameter, but we can remove it by some transformation. And this is lattice potential modified KdV. So we have 4. So each of them can be matrix lattice potential modified KdV. And this is NQC equation in matrix form, and we have one and also another one. And this is Schwaden KdV, and this is a Q30 in matrix form. Either these or these. There is a transformation between NQC equation and it. And also some matrix equation in discrete Booth-Nash type. So I use this kind of notation. This is some Yarmos notation. This is one, and this is another, and this is something like B2 equation in your paper. This is A2, and this is C3. Okay, just summary for this talk. We use the roots of polynomial, this kind of polynomial G omega k, to define discrete dispersion relation, and also define the plane wave factor. So these two equations are used to define plane wave factor, but k and k prime are the roots of this polynomial. And then the Sylvester equation is here. It is also necessary, and but finally the simple form of the Sylvester equation is this. Gamma is canonical form. So what kind of role that the Sylvester equation play? Actually, if you look at the tau function definition of tau function, this is a determinant. But this is a scalar case, but not a matrix case. So far, I don't know how to define the tau function in matrix case. But if you look at the scalar case, and the tau function is defined in this way. So I would say the Sylvester equation is used to introduce tau function for discrete case. I finished the talk.
So, any questions?
No question, I can sample.
Now, you mentioned that the tau function is related to these constructions. So can you actually do all what you did in parallel in the bilinear formulas?
No. No, first actually is I think we need some relation for this tau function. If I don't have this tau function, the equation for this tau function, then I don't have bilinear form.
Not in a matrix form, but in the first part of your talk.
Even
Because
no, I think so. I think so. It will be more easy if we give up the whole Cauchy matrix procedure. We just look at the solution in the bilinear form. Then we can do some trick in the causality.
Yes, that's what I'm saying. Okay. Any further questions, comments, remarks? No, then let's thank our speaker.